Hello everyone, from the world of industrial automation. My name is Artem Melnik, and I am a software engineer with 15 years of experience in developing firmware and software for programmable logic controllers. Let's develop an automated control system for an industrial dry heat sterilizer. All the devices mentioned are connected to each other through a router that has internet access. The thicker the metal insulation walls, and the lower the thermal conductivity coefficient of the insulation material, the better the sterilizer chamber retains heat, and, as a result, the less electricity it consumes. The larger the chamber volume, the more instruments can be sterilized in a single load, but the longer it takes to heat the chamber to the target temperature. And as a result, we get higher energy consumption and cost compared to a sterilizer with a smaller chamber volume. The sixth parameter is the sensor type. We can choose different types of sensors, and for each type, we can also set the inertia or time constant of the internal temperature sensor. The higher this parameter, the slower the sensor responds to changes in the actual temperature inside the sterilizer chamber. The sixth value is the actual temperature inside the sterilizer chamber. As you can see, the temperature sensor readings lag behind the actual temperature during the heating phase, because when the heater is on, the frequency of changes in the actual temperature increases. This difference fully corresponds to the inertia or time constant of the internal temperature sensor set in the settings. For the current 15-liter sterilizer model and the current emulator settings, our thermal balance model is very close to the actual physical process of temperature change inside the sterilizer chamber. Let's take a look at the structural diagram of the equipment connection. As we mentioned earlier, instead of a real sterilizer, we are using an emulator based on equipment from akYtec, the SPC210 touchscreen programmable controller and the MU210 502 analog output module. This module allows us to emulate up to 6 temperature sensors, since it has 6 analog outputs, each of which can be connected to a separate analog input of the MV210 101 module with a 4 to 20 mA signal type. Our emulator currently supports simulating just one temperature sensor. To do this, we connected the first analog output of the MU210 502 module to the first analog input of the MV210 101 module according to the diagram shown in the picture. We connect the plus 24 volts terminal of the external DC power supply to the terminal of the first analog output A01A with a red wire. We connect the 0-volt terminal of the external DC power supply to the terminal of the first analog output A01C with a black wire. We connect the terminal of the first analog output A01B with a brown wire through a 400 ohm resistor rated at no less than 0.5 watts to the terminal of the first analog input AI12. We connect the terminal of the first analog output, A01C, to the terminal of the first analog input, AI11, with a black wire. Let's move on to the improved version of the emulator project. We'll declare the following variables, which we need to store in non-volatile memory, that is, retain. Even if the SPC210 loses power, all these settings will be preserved. Sterilizer chamber wall thickness in millimeters, thermal insulation thickness in millimeters, insulation material, thermal conductivity coefficient of the insulation material, usable volume of the sterilizer chamber in liters, mass of metal medical instruments. This directly affects the heat capacity of the chamber. The heavier the load, the slower the temperature changes. Ambient room temperature, number of external sensors in the current sterilizer modification, base temperature inside the sterilizer, number of internal sensors in the current sterilizer model, array of internal sensor types. The emulator supports installing from 1 to 6 sensors. This is necessary for designing different sterilizer modifications. The inertia or time constant of the internal sensors, measured in seconds, indicates how quickly the sensor responds to changes in the actual temperature inside the chamber. A value of 0 means the inertia is determined automatically based on the sensor type. Number of heating elements in the current sterilizer model and their types. The emulator supports installing from 1 to 6 heating elements. Maximum power of the heating elements measured in watts. A value of 0 means the power is determined automatically based on the type of heating element. Heating element power control mode. Maximum power position of the heating elements. Write in the comments why we add prefixes to the name of each variable. Now let's declare the variables that do not need to be saved in non-volatile memory. Start/stop emulator button, main task call interval measured in seconds, average ambient temperature from external sensors in degrees Celsius, approximate surface area of the chamber in square meters, heat loss coefficient of the entire chamber through insulation in watts per degree Celsius, heat capacity coefficient per liter of an empty chamber in joules per degree Celsius, chamber load factor, effective heat capacity of the chamber taking into account the load of instruments in joules per degree Celsius, active total power of all switched on heating elements in watts, actual physical air temperature inside the chamber in degrees Celsius, actual physical air temperature inside the chamber during the previous controller cycle in degrees Celsius, net power or heat balance, active total power minus heat losses in watts, heating rate, cooling rate in degrees Celsius per second. Access flag for the setting maximum power position of heating elements. True. Access is denied for setting a new value for the maximum power position of the heating elements. Readings from external temperature sensors in degrees Celsius. Readings from internal temperature sensors in degrees Celsius. Analog output control signals for transmitting sensor readings to the main project. Current power position of the heating elements. Looking at the variable descriptions, you may have noticed that our algorithm will support different types of sensors, heating elements, and insulation materials. It'll also support installing from 1 to 6 internal temperature sensors and heating elements in the sterilizer chamber. This is so we can design absolutely any model of sterilizer and not be dependent on a specific supplier of insulation material, sensor, or heating element. Now let's move on to the surprise section and show how to disable the user's ability to change settings when the power button is turned on. To do this, in the visualization editor, select all the necessary graphic elements. You can do this by holding down the Shift key and selecting each of these elements. Then right-click on any of them and choose the Group command. And now we have another entity appearing in the list of elements, called Group, which includes all the graphic elements we selected. In the group's properties, we link the deactivate inputs parameter to the variable of the start-stop emulator button. We also link this same variable to the variable parameter of the button itself. In the next video, we will take a detailed look at the code for the emulator's operation algorithm written in ST language and thoroughly review all the visualization components of our improved prototype. Now, I suggest you identify any shortcomings in the prototype that you noticed and propose ways to address them. Our channel has the exclusive right to offer a 35% discount on the purchase of SPC210 and input-output modules from akYtec. To get this promo code, simply follow the link below to our WhatsApp or Telegram channel, where you'll find my personal contact in the channel profile. You can send me a direct message with the word promo code. But I want to point out that this promo code is only valid for 24 hours, so please contact me only if you have already added the products to your cart on the akYtec website. And one more pleasant surprise for those viewers who purchase the SPC210 and send me the serial number of their controller in a private message, I will provide all the CODESYS projects used in our channel's videos for free. You can also subscribe to our WhatsApp and Telegram channels so you don't miss announcements about upcoming videos, and of course, so you can always get a promo code for a discount on akYtec products. And don't forget to subscribe to our YouTube channel so you don't miss future videos, and give this video a like if you enjoyed it. That's all for now. See you in the next videos.